off to recess. Now, we are a lesson or two behind due to various disruptions. So what I will be asking you to do either tonight or tomorrow night, probably not tomorrow night because of swimming, I'm going to ask you to catch up by watching one of last year's lessons. And we'll treat that as a lesson, okay? Because we should really be starting specific heat capacity this week. We should have finished the temperature scales last week, all right? So it's quite important. It's quite important that you treat that as a lesson and you watch it, because we're going to be doing our first lab on Wednesday, and then with that, you're going to have the validation a week from that day. So if we collect all the data this Wednesday, and then you'll have a quick validation on that the following Wednesday. Okay? So let's just finish off this booklet. We've got some cool videos maybe we'll get to, but it's important that you understand that there are various types of thermometers, a few of which you can explain how they work using that kinetic theory of matter. Okay? Now, did I ask you to scribble down the thermometer? Where was he? Huh? Nope. Where did I draw my thumb and finger? Huh. Ah, there he is. Okay, cool. So just recall, a simple question as explain how a thermometer works might be worth 5 marks, and you've got to write a wonderful paragraph as to what's happening. The heat flows into the alcohol in the bulb. It causes the kinetic energy of the particles to increase. As temperature is a measure of the mean translational velocity of particles in a substance, temperature goes up. They're imparting more momentum to their neighbours, and hence more force, and hence move further apart and occupy a larger volume. And since they can't move in left, right, forwards or backwards, they have to work up the capillary. So there's a lot going on there, okay? So you need to be able to put all of those processes down in dot point form to explain those explanation questions. Now, I just wanted to quickly revise that. Let's go down to the various types of thermometers. Now, the first few can be explained, and I'll just write it here, using the kinetic theory. Okay? So the great thing is that the temperature of a substance is directly proportional to the change in length or the change in volume. So for example, the liquid spirit thermometer, its volume is definitely changing, and obviously if the cross-sectional area of the capillary is constant, then the only way it can increase its volume is by increasing its length. Okay? So we've got a very nice direct proportionality. It's the change in temperature, not one temperature on its own, but the change is proportional to the change. So if I had a delta T of 2 degrees and a delta T of 4 degrees, then we would expect our changes in length to be directly proportional. And so nicely for us, Mr. Angus hasn't provided me with any examples of thermometers. Alright, so here is our glass thermometer. We're probably not even going to play with these because they're not very precise. We can get better instruments that can give us a higher precision in our measurements, okay? But there's a direct proportionality, which is nice. The next one is the absolute pressure. Now, this is similar to what William von Baron Kelvin Lord the first, whatever his name was. He was using this kind of absolute pressure thermometer. So this is a fixed volume, all right, and it's at a certain temperature, and the particles are pushing on this pressure gauge. And so very quickly, if we were to cool our thermometer down, hopefully, as heat leaves. You can start using those dot points of explaining what's happening here. Why does the pressure decrease when it's plunged into ice water? You say as heat leaves, there is a difference in temperature, so heat leaves the warm air inside the bowl, the particles in there lose kinetic energy. As temperature is a measure of blah, 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 their velocities drop, they're imparting less momentum, less force to their neighbours, hence pressure drops. Okay, so all of those dot points. Now that's not a very large decrease. We can go the other way. Remember I said heat flow is omnidirectional. We can have heat flowing out or we can have heat flowing in. And all you're going to do is reverse those verbs. Okay? Heat flows in, the particles gain kinetic energy. Temperature increases, they have more momentum, impart more force, and hence a greater pressure. Okay? So I would encourage you to familiarise yourself with writing down those kind of dot points to explain. Directly proportional again, which is incredibly useful for us. Okay? Oh, hang on, I believe that was our fixed volume thermometer. How are we going with the OneNote?
It's still going.
Still going? Okay. All right. Next, these ones are a little bit different. They have different processes. We can't really explain the kinetic theory. This has electrical resistance. So we have a thermistor here. Make sure I have the right device. Here's our thermistor. And it's directly proportional to resistance. So if I was to heat up this little wire, then hopefully we would see... hang on, let me just cool it down and see what happens. Cool down our piece of wire. What are we measuring? We're measuring resistance seems to be going up. If we were to heat it, resistance seems to drop. I thought it would have been the other way around, but whatever. It's directly proportional. Then we have our thermocouple, another weird phenomena where if we have two different metals and we wrap them around and produce a little coupling of wire and we heat them, then we can encourage electrons to move from one side of the wire to the other by thermal excitation, and that will establish a voltage across the wire. And again, it is directly proportional. What I'm getting at, these symbols here, very, very important. Because I am going to put a question in your first test that uses the calibration equation. And this can be used for any. Now, we've got capital T's there, but if we have an unknown temperature, we need to use our centigrade scale, which is what Celsius used. Boiling point and melting point of water. 100 and 0, but we can see it in a variety of ways. So we could get our unknown length if we measure the length of a capillary, then we can determine the unknown temperature. Or if I used a thermistor, we could measure the resistances. Oh, that should say 100, not 0, because that would be bad. Or resistance. Or we could use a thermocouple or pressure. You get the idea. We could use any. So an unknown voltage of the voltage of an unknown temperature. We would then need to know the voltage at 100 and the voltage at 0. I can't talk and write at the same time. Just give us a second, and then some weird things are appearing on my screen. Don't know what that is. Okay, so this will always give us our unknown temperature. Yes, Hugo.
Could you do like a real life? Give us like a real life example?
Absolutely. We're going to fill this page with a couple of examples. Okay, and we might even let's get this sucker boiling, and we might be able to calibrate. Everything's just covered in water. Great. So, you may have recalled doing this in Year 9 physics. where we gave you an uncalibrated thermometer, basically an alcohol in-glass thermometer without any scale, and you placed it in boiling water, you put a dash, you put it in freezing water, you put a dash, and then you tried to figure out the unknown temperature. Okay, so let's do an example. I've got here, could we just add some values? 13.2 centimetres when placed, and we're going to measure it from the bottom of the bulb. When placed in ice water, we get 13.2, and when placed in boiling water, it rises up to, let's go, 27.3, and then we place it in an unknown substance of an unknown temperature, and somebody give me a number.
42.
Madness, 42.0. Let's just measure to the same precision, okay? Now, the great thing about measuring it from the bottom is if we go below our scale, it will give us a negative value, and if we go above our scale, it will give us a value above 100, which is exactly what Zach chose. So let's find T unknown equals... No, you just gave me a length of 42. So let's figure out what temperature that corresponds to. So we'll go length unknown, take L0, over length 100, take length 0. Okay? So we'll throw all of our values in. 42.0, take 13.2. Okay? Now, have a look. With remembering all the stuff we learned in week 1, let's look at our subtraction. We're going to express our answer to the decimal places. So we're going to have a 1 decimal over a 1 decimal. Could you just give me the intermediate step? What is the numerator equal to?
28.8.
28.8 divided by 14.1 times 100. Now, let's just do the next intermediate step. Now we are dividing, okay? And so we're going to express our answer to 3 significant figures. So could somebody tell me what this is to 3 significant?
2.04.
2.04 times 100. Now, don't be fooled. Even though we are multiplying, this was not measured. There are exactly 100 degrees between boiling and melting. All right? So don't be cocky and go, 1 sig fig, I'm going to put my answer to 1. No. This is not a measured value. It is a discrete number. Okay? So sometimes students get a little bit tempted to just continue looking for sig figs. You've got to analyze what values have I got that are measured, what values have I got that are discrete or known. So 204 degrees Celsius. And the precision of our measurements has enabled us to leave that to 3 significant figures. Okay? Would you like to do uncertainty?
Yes.
Yes, let's do it. We've got time, we're all friends. Now, this isn't too tricky. Have a look at what we've got. At the top here, we've got L take L. Okay? So, we need to go to rule number 1 of combining uncertainties, which states when adding or subtracting measurements, we add the absolute. So we need to add the absolute uncertainties of our measurements. Now, here's the thing. I gave you these numbers, but I reckon that we're going up in 1 degree intervals, because remember, when taking measurements of analog scales, you're allowed to estimate 1 order of precision higher. Okay? So this 0.3 would be a guess. If I zoomed in, or this, 42.0, that might be 42, that might be 43, that might be 41, that might be 40. Okay? So that 0 is a guess, which means that our uncertainty is plus or minus half a degree. All right? And so when we come over here, let's just, if we have the room off to the side, we'll say, here, you would say plus or minus 0.5 degrees plus 0.5 degrees. Okay? Sorry? Oh, it was centimetres. Sorry, yeah, oh gosh. It is centimetres. Let's suppose we measured it with a ruler to the nearest centimetre. Okay? Good spot. Sorry guys, it was actually measured length in centimetres. So just right here, assume okay, in which case that is still an estimate. Okay, apologies there. It is an estimate, and that should have been 0.5 centimetres, not degrees Celsius. Thank you. All right. So over here, plus or minus 0.5. Plus or minus 1 centimetre, or using the addition rule, 1.0. And then the same here. It's going to be plus or minus, same rule. When adding or subtracting measurements, we add the absolutes. But now, we've got our absolutes, so I know that my difference in length is 28.8 plus or minus 1 centimetre. My scale from 0 to boiling is only 14.1 plus or minus 1. But look now, we are multiplying or dividing our measurements. So that's now rule number 2, which states when multiplying or dividing, we have to add the percentage uncertainties. Okay? So we need to get what is 1 as a percentage of 28.8. Whoa, slow down. So I'll just write total percentage uncertainty equals 1 over 28.8 times 100 plus 1 over 14.1 times 100. Do you want to just give me the total if you've calculated it? Cool. 10.56%. Okay, so again, when you're combining your uncertainties, it's okay to have a little. You could go to 3 sig fig when we're combining our uncertainties, because remember at the very end we're gonna round it to the same precision of our measurement. Okay, so this is our percentage uncertainty. We now need to express this 204 plus or minus degrees Celsius plus or minus 10.56%. We're then going to convert it to an absolute uncertainty. What do we get? 21.54. And then lastly, we express our error to the decimal places of the measurement. So we need to round this to 0 decimal places. So it's going to be 204 plus or minus 22. Oh, geez. Slow down, laptop. Again, perfect example here. A lot of students get caught out. We stop. A lot of students get caught out when if you've got a delta T, which we will have in our thermal experiments. If you're taking a measurement of temperature, subtracting it from another, remember you've got to add the absolutes. A lot of people say that delta T is plus or minus half a degree. Actually, subtract that, so it's 2 lot. You've got to add them, so that often it's plus or minus 1.0 degrees. Yes?
Well, the plus or minus 22 degrees.
Yep.
We do that as 0 decimal places or 3 sig figs.
Well, that's 3 sig fig.
Yep.
This is 0 decimal place.
Okay.
Okay?
How do you decide?
So this came from the rule of when we multiply and divide, we express our number to the limiting sig fig. So it just happened to come out as 3 sig fig. But then our absolute, the error or the uncertainty is a different rule. That last rule, you quote your error to the precision of your measurements. You quote it to the decimal places. So we're taking all of these rules and putting them in. Okay? Now, again, 11% is far too high of an uncertainty, and basically that is because I used a dodgy ruler. If, centimetre divisions, that's crap. Get a ruler that has millimetre divisions. Now, we're not going to do the equations again, but follow my logic here. If we increase our precision of our measurement by a factor of 10, then over here, our absolute uncertainties decrease by a factor of 10, right? Which means our total percentage uncertainty decreases by the same factor of 10. So instead of 10%, we're down to 1%. And then at the very end, our absolute uncertainty would also decrease by a factor of 10. So we could get it to 204 plus or minus 2, which is a much more precise measurement if we had started off with a better ruler. Okay? So again, always choose your measuring devices with the higher precision. Oh, I should have just told you. Oh, I've been ignoring that update for the past... Oh, hang on. You updated my iOS. Yeah. I've been ignoring that for like the past 15 months. Just remind me tomorrow, remind me tomorrow. Okay. So, remember, I told you there will be a question on this kind of topic. Okay? Using the calibration equation to determine the unknown temperature. We need our two fixed points, which we still use T0 and T100, even though we know that they're not that reliable. Okay? Expect a question like that. I'm not going to tell you whether we're using a length or a resistance or a volume, but they're interchangeable. The volume at 0, the volume at 100, and the volume of your unknown object. Yes?
Are we expected to memorize whether liquid spirit fluid is a link to length and stuff like that, or not?
With the proportionalities?
Yeah.
No.
So it was saying the question.
You'll be told whether it's a resistor or a thermistor or a thermocouple. Okay? We'll talk about this one later on in the year. As we approach the first test, the reason we have that test there and not just one topic test is because the parent-teacher interviews are always week 4 or week 5. So we need to have something assessed from you to discuss with your folks. All right? That's why we have this little intermediate test. If you go on to Nexus, you will see the past 4 or 5 years, it's called Thermal Physics VT, Validation Test. So capital V, capital T, that's kind of your interim test. Okay? I might just get you guys working now on these... No, wait, I got you guys to do this for homework. Did you do all of these questions? Yes. Cool. All right. Let's jump in. I think we're good here. We've looked at the different types of thermometers. We looked at the proportionalities. We did the calibration equation. Let's jump into specific heat capacity, please. So could you go to the next page? And I would hope that you get the following. All right. So, what I'm going to do now, if we can spend the next 20 minutes on this, your homework might only be watch the last 15 minutes of a video from last year, just so that we claw back a lesson. Okay? There were some cool videos that I wanted to show you, but you can watch them in your own time. Now,
I probably will ask 3 questions at the moment. 8, 9, and 10.
shall we go through those questions? See me at recess, we'll have a look. Or come to the physics help session every Monday at lunch in this room. Okay? Now, you would have covered specific heat capacity in Year 9 again. Basically, they are going to store or respond to heat, which is the transfer of energy, in different ways. When you give a molecule energy it can either jiggle faster or it can store that energy in its bonds. You actually get the atoms can sort of start vibrating backwards and forwards like a spring. And then they can rotate about those bonds. They can oscillate in various modes. So if you just had a single atom that all it can do is just bounce, it's going to jiggle faster if you gave it a certain amount of energy. But if you gave a molecule, a really complicated molecule with lots of different atoms in a different shape, if you gave it the same amount of energy, it might be able to store that energy in various ways, in various modes. Okay? So not all substances will change their temperature by the same amount. And so you will have a list, and I've probably given you a list of specific heat capacities on the next page. Okay? So different elements and molecules and compounds have their own thermal properties. But let's go back to the proportionalities. Now I want to start with what delta T is going to be proportional to. So could you please write delta T equals T final minus T initial. Just write that for me now. Anytime you see that character, which is a capital delta, it means change in. It means final minus initial. So you could have delta M, change in mass, delta V, change in velocity. Delta T is change in temperature. Okay? Now the proportionalities are as such. Okay? It's proportional to the amount of heat that is supplied. If you give your particles double the energy, they will jiggle at double the rate. They will have a temperature difference that will be double. So that hopefully makes sense. The next, it's proportional to 1 on m. It's an inverse proportion to mass. So obviously let's put down our Q is heat measured in joules. M is mass measured in kilograms. Now have a think. If you gave some heat to a mass, you're looking at number of particles. If you double the mass, you're basically sharing that heat amongst twice the number of particles. Each particle receives half if we double the mass. Okay? Are we good?
Yeah, you'll probably just have to log
To one drive. Awesome. Thank you so much for that. Cheers. Oh gosh, it's loading it all up. So this makes sense. It's like sharing. It's if we're distributing energy over more particles, then each particle will have less jiggle because they're going to have less kinetic energy. All right. So let's combine these. Oop. We would say that it's proportional to Q over M, if proportional, not equal, proportional. Now we want some constant. Now I've got this written the wrong way. We could say that the Q required is proportional to, well, we times both sides, it would be M delta T. All right, so I've just rearranged our proportionalities. The amount of heat required depends on how much mass you have. The more mass, the more heat you have to supply. And what delta T you require. If you want more temperature change, you'd have to throw more heat at your substance. Now, to get rid of that proportionality, we're going to add what's called a constant of proportionality. Now, that constant is the specific heat capacity. Okay? Here are some notebooks that you might want to get started with. Yes, 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 yes. Yes, yes. No, 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 no. Now, again, this constant, basically what it does is it gets the units correct. Because have a look. We have here something that is in the units joules. And over here, we've got kilograms and Kelvin. Okay? They don't equate. A joule is not a kilogram Kelvin. So we need some unit, some special unit that's unique to each substance and basically converts kilogram kelvins into joules. Okay? So that is our little constant of proportionality. You will see it written in your textbooks as Q equal... Why is it such a big box? Oh well. Q equals MC delta T. Okay? MC delta T. It rolls off the tongue quite nicely. Q equals MC delta T. Okay? We could then rearrange for any unknown variable if we wanted to. If I wanted the specific heat, well, that's Q divided by M delta T. The reason I want to write Q over M delta T is because we can get the units now for our specific heat capacity. It's going to be joules divided by, our units for mass are kilograms, and the unit for delta T is Kelvin. So our unit for specific heat capacity, which is way up here, just right here, delta T equals change in temp, which was Kelvin. Our C is specific heat, and it's joules per kilogram per Kelvin. Okay, so this just, if you multiply M delta T by this, the kilograms and the kelvins all cancel and out spits a number which we call joules. Okay. If we go back to our definition that I've placed up in purple at the top, essentially we could just figure out, if we set M to 1 and delta T to 1 in this equation at the bottom, then basically Q just equals C. C equals Q. If you've got 1 kilogram and 1 Kelvin. So it makes sense that the definition is now the energy, or the heat energy required to raise a kilogram of a substance by 1 Kelvin. Or 1 degree Celsius, because the scale steps of both those temperature scales are the same. Okay? So, over the page. In fact, hang on, let me just see. Sorry, bear with me. I just want to make sure I haven't skipped anything that I may have written down. Oh, okay. Yes, I've got some room here. Here's what I want to quickly show you. We can take this equation and expand delta T, and it will be important to do so in future lessons. We could write this as Q equals MC. That's it. TF minus TI. So we could then write equals MC TF minus TI. Because occasionally we might be given the initial temperature and asked to find the final. Or we might be given the final and asked to find what must the initial temperature have been. Okay? So just be aware of that, and let's highlight that. Okay? One last thing, because I like using my buddy dimensional analysis, let's just check. If we take the units of mass, which is the kilogram, if we take the units of the specific heat capacity, which is joules per kilogram per Kelvin, and we take the units of our change in temperature, Kelvin, we can see the kelvins will cancel, the kilograms cancel, and we're left with a unit of joules. Okay? Now this is called dimensional analysis. Alright? This is a very handy tool. It is not in the syllabus. You two boys, do you want to go outside and talk? No. Shush. It is not in the course. It is not required. It is not assessed. But it is an incredible, useful tool for a Year 11 and Year 12 physics student. I remember I was at Murdoch University in my probably second year, and my friend Pook, his name is actually Richard, but his nickname was Pook, P-O-O-K, he came racing in because he'd just come from his maths maths course tutor session, and he goes, "Have you heard about this thing called dimensional analysis?" I'm like, "No." He goes, "It's awesome." And so he goes, "Look, I'll show you." We raced up to the whiteboard in the common room. He goes, "Oh, give me an equation." So I said, "Oh, I don't know, Q equals MC delta T." And so he started putting all of the units in brackets, and then cancel. You could prove, or at least show, that the equation was correct, because the units will also simplify to show you what your unknown variable should be in. Okay? And we will use this again when we get to motion, equations of motion, forces. I am going off on a little side mission here because this is fun. Let's look at acceleration. What are the units for acceleration? Meters per second squared. Thank you. Now, if I said F equals ma, that gives us a Newton, which is the unit of mass times the units of acceleration, which gives kilogram meters per second squared. So Isaac Newton wasn't that arrogant that he named the unit of force after himself. And in fact, back in the late 1600s, early 1700s, SI units weren't even around. He would have been playing with feet and pound and seconds. So he would have had pound feet per second squares. All right? So a Newton is called a derived unit because it is derived from the fundamental units of mass and space and time. Okay? Next, you could say that energy is, the transfer of energy is work, which is F times S. So if I then said, well, let's take our units of force and multiplied it by the unit of displacement, we get kilogram meters squared per second squared. And that is our unit for energy. Okay? So again, it's a derived unit of the fundamental units of mass, distance, and time. Okay? So any time, if I said that we supply something with 100 joules of heat, I could just as well say I supplied the substance with 100 kilogram meters squared per second squareds of heat. It means exactly the same thing. Okay? Unfortunately, temperature is a bit weird because Kelvin, you can't really show dimensional analysis. Just come in and sit down. I'm sure you had honourable excuses. All right, over the page. In fact, I might not give you any homework. You might not have to watch any videos. How much heat? Q equals question mark. M equals 5. We're raising, so our delta T is given as plus 10. Okay? And we're told water, and so we're going to take the specific heat of water down here, liquid water, that's what we need. So, again, if you are not already doing so, please write all of your variables on the left-hand side. And just be careful here that, remember we said that heat can flow one way or the other. And it's going to be shown by the sign of delta T. If delta T is positive, that means that temperature is increasing. That means we are gaining heat. Okay? If we were reducing the temperature, then delta T would be negative. And that's going to show itself in the equation. So you pick the right equation. Q equals MC delta T. And we get plus... now, too sig fig for this, but let's just go 2.1 times 10 to the 5 joules. In fact, hang on, I'm going to just start over. Would somebody mind calculating this for me in their calculator? And just tell me what everything is? No, but just the full number, the whole number. 210,000. Okay. In fact, that is to 2 sig fig. 2.1 times 10 to the 5 joules, and I'll just write in the bracket here 2 sig fig, because we were given a number to 2 sig fig. All right? Yes, what's up? Why is it 4,180? Excellent question. Bugger. To 3 significant figures, it's actually 4,180. Thank you for spotting that. In your data sheet, it is given to 3 sig fig. So would you mind just going down here, scribbling out that, and writing 4,180? All right, because you will have to use values in your data sheet, and you are given it to 3 significant figures. Yes, question?
Do you have to give it a scientific information?
You don't have to. In this case, we didn't, because that number was already to 2 sig fig. But if your calculator threw out a few vestigial decimals, so if your calculator spat out 210,536 or 214,536, you would then have to round. But we didn't need to. Conveniently, 210,000. So just a little note here. If delta T is positive, Q is positive. And so that means we've gained heat. If delta T is negative, then Q is negative, and that means we've lost heat. Let's try and draw that a little bit neater than what I've done. Okay, it might not seem important, but as it gets more and more difficult, and we're starting to use some more complicated equations, it is important to determine the value of the Q, positive or negative, whether we are gaining or losing heat. Okay. Now, again, if you notice, water in its liquid state is one of those rare substances where it has the highest specific heat. You need the most amount of energy to change a kilo of water by 1 degree than any other substance. Okay? And that has to do with a number of things. The shape of the molecule, the freedom that it has when it's in its liquid state. Water is polar, which means that even the ends of the molecule can basically store elastic energy. So you can throw energy to a sample of water, and rather than make it jiggle faster, it's just going to store it elastically between the bonds between the hydrogen and the oxygen, and even the bonds between the molecules, positive and negative, like the springs. So I like to visualize water as these molecules with all of these springs, and as you start sort of shaking them, all you're doing is compressing the springs rather than making the molecules shake. So water is a very special exception, that it has a very, very large specific heat capacity. You've got to throw a heap of energy in to change its temperature. All right, next two. I'd like you to emulate what I did. Could you please highlight, underline the important things? Okay. Write your variables on the left-hand side. And here's the thing. I know that the delta T is plus 380, but you cannot just write plus 380, Zach Stanley. Zach Stanley? You're right? Yeah. Wake up. You can't just write 380. Because that means if I do mental maths in my head, I have to write it down on the page. It sounds a little bit pedantic, but you have to show it all working out. So if there is a number that appears on your writing that's not in the text, you have to explain or show how you got to that number. So write down 400 minus 20 equals plus 380. Seems a bit silly, but that's what we need to do. Same for this one here, mass. Okay? So get going for those, please. SAWO. If you've ever seen this on a test or piece of marked work from me, it means show all working out. So I'll often give back pieces of work to students with SAWO. That means that you haven't shown all of your working, you've skipped steps. Okay? Copper is 390. No, we don't want C, we want M. Oh yeah, this one's a little bit tricky. It should be 1 sig fig. If you looked at this, let's just get to it in a moment. Let's just solve this. That should be a C. All right, now, okay, here's the problem. When I made this question, I wasn't very nice. If you followed the rules, I'd look at that and go, that's been given to 1 sig fig, so I'm going to express this as 0 to 1 sig fig. I'd have to round that down. Obviously, no. If Mr. Murray was making a test question, I want all of my values to be 3 sig fig. So to get around that, in a test, I would probably write 5.00 times 10 to the 4 joules. By doing that, I've now given you a value to 3 sig fig. And then down here, I would probably change that to 20.0 degrees Celsius. And this one, either 4.00 times 10 to the 2, or I could give you 400.0. I could add an extra. In which case, we're now at 3 sig and 4 sig. Okay? So, look, I apologize. That should really... We're not going to round it to 1 sig fig. Lastly, hold on. These numbers are all significant. So again, do not look at the specific heat capacity of air and go 1 sig fig. No, all of these numbers are significant. Okay? So they, in your data sheet, it's going to say 1.00 times 10 to the 3, or 2.00 down here. Okay, so this number in your data sheet will be given to 3 sig fig. How do we get around that? We use scientific notation. So 2.00 times 10 to the 3. Okay. So again, don't be cocky, but I agree that really I should have given you these values all to 3 sig figs. Okay. All right, gents and ladies, that is time. I didn't check your homework. When do I see you next? Tomorrow, period 6. Show me your homework tomorrow, period 6, please.